Hi everyone. My name is Arseny. There were great talks about circuit breakers. Now I will talk about how to build a system that will actually trigger these circuit breakers. I mean, some system that works off-chain, that watches some transactions, watches some invariants of smart contract, and that can observe the moment when, for example, a hack is happening or something unexpected has caused some loss in the protocol. A bit about myself. I have been working for 10 years building similar stuff. I mean, I was a developer and head of development for a product that essentially provided the same approaches, but for websites. I mean, a web application firewall. And we decided that we can apply similar approaches to detect DeFi exploits. And this is how I will spend these 16 minutes. Firstly, I will talk about the motivation and our goal. Then we will go to the architecture of the solution. Then we will discuss how did we implement this architecture. And then I will share some techniques of exploit detection and some results that we got after we were running this system for at least, for 6 months. Okay, so our goal was to detect DeFi exploits. I think it's quite important topic nowadays. There are constantly hacks, and many of them are unknown to people because nobody watches all the transactions, nobody understands all the call traces, and cannot just catch all the patterns that can be a hack and an indicator of hack. So we decided that we want to try our best at this to find something that resembles a hack by watching some indicators that we receive by processing all the data essentially from the blockchain. So we decided that we don't use ready-made solutions because they were somewhat clunky, and to be honest, not so many open source projects are out there, except for Forta, I guess. And our approach was to just grab all the data that we can see, that we can gather from the RPC endpoint, and to ingest it into our system. So as I said, I'm coming from Web 2 security, from traditional cybersecurity, and in this field, the monitoring solutions are very widespread. They are very developed. There are open standards of how, for example, threat intelligence is shared. But in Web3 currently, there are not so many good practices implemented. I mean, not so many standards that you can follow. So everything essentially is from scratch. So this is the architecture of the systems that we decided to build. So the essential part is ETL. This is the black circle, square. ETL means extract, transform, and load. This is basically the part that extracts all the data from the blockchain, which does data enrichment, and which sends all this data to the next to the pipeline. After ETL has extracted some data, it splits this data into different streams. These streams can be transactions, logs, contracts, call traces, anything. After we receive this data in separate streams, we can combine the streams in some jobs that can process these streams, join them or calculate some stuff, and basically detect some exploits or some invariants being broken. So this is basically the main logic component. And after an exploit, for example, is detected, we of course log it to the database, which is a source of data for BI dashboard and for threat intelligence feeds. So as I mentioned, ETL stands for extract, transform, and load. And for this task, there are not so many tools. The most suitable ones that we considered were Ethereum ETL and a newer tool developed by Paradigm called Creo. Both tools have their advantages and disadvantages, but we decided to choose Ethereum ETL because it allows to work on streaming data. I mean that it can constantly receive new blocks and push it to the upstream system. Creo does more things. For example, it can extract state diffs, balance diffs, storage diffs. This is very important data that we don't analyze currently, but I guess in the future when Creo adds streaming capabilities, we will consider switching to this new tool. So Ethereum ETL out of the box also didn't satisfy our needs, so we had to modify some parts, add some new functionalities. For example, it lacked some bulk processing. It's very important for us because we are using cloud RPCs, and the spending of credits is really important. So we added missing parts like extraction via ETH block receipts. We also integrated DeFi Lemma API, so we can calculate balance changes in dollars in real time. Also, we added the extraction of cold traces because Ethereum ETL only supported parity style traces. We needed guess Go Ethereum style traces. And I think the most important part is that we integrated GigaHorse toolchain, a tool developed by GDOP. This is a really powerful framework that allows you to analyze the bytecode. The bytecode analysis is very important when you wanted to find a malicious exploit because, of course, they never never reveal their source code. So you need to operate on the bytecode level. And for that, we used GigaHorse because it allows you to write custom analysis. Unlike, for example, Heimdall, which we also considered, this is also a newer tool, but it can be customized, but you need to write you need to change the underlying functions and structures of Heimdall. So GigaHorse was our choice in this regard. We replaced the built-in EVM JASM. This is a very old project that is used by Ethereum ETL right now. We replaced it with GigaHorse, as I said. We also wrote some custom analysis rules to detect exploits that we run on each new contract deployment that we observe. I guess GDOP team also does this for their product. But their rules, of course, are not open source, so we had to write our own rules. And we basically detect exploits after this analysis based on some specific features. For example, some exploits, well, not some, many exploits do not have that many functions. From what have we seen, it's usually not greater than 10 functions. Usually exploits just have 5 or 6 functions. One of them is called like do it or exploit or start, like this. I must say that at the current stage of the exploit development, hackers are not very sophisticated. They do not obfuscate their code. They name their functions with easily guessable names. So I guess in the future, as soon as hackers understand which techniques are used against them, they will step up their game and will employ more sophisticated techniques to hide the presence of some indicators inside their bytecode. And other features of exploits are on the screen, so they are high rate of unknown selectors, of course presence of flash loan selectors, lots of external calls because they need to interact with other contracts rather than updating their internal state. They never emit events because exploits do not need to emit events, basically. And what is surprising, they often leave debugging symbols inside their bytecode. For example, console log calls that is an easy indicator for such systems to detect exploits. So, more about the system itself. So, we have a stream of data in different topics, in different streams. So, we needed a system to build a system that can process all this data. And this is our solution. We used two Apache projects. One is Kafka for ingesting data inside topics. So Ethereum ETL pushes data to Kafka. And then we use Apache Flink. This is a real-time streaming processing system, open source one, that allows to perform stateful computations over streams of data. And it allows to do that in just SQL, and this SQL works in real time. And what is more important, that it supports CEP, complex event processing. It means that it can detect specific patterns in the sequences of items of data, or in, for example, in call traces and so on. So in the high level, this is how it works. So we just describe the sources, our source data points like transactions, contracts, logs, token transfers, call traces, and so on. Then we define the sinks where the data should go, should be locked. And then we execute the SQL queries with our logic that basically gets the data from the sources, processes it, and pushes the results into the sink. This is how it works, just to give you an idea what is a continuous SQL looks like. So we create a table for token transfer in this example, and you can see that this stream is continuous. So it constantly updates balance change field, so we can observe balance changes in every transaction in USD, and this is a great indicator for observing large inflows or outflows of crypto inside the transactions. This is the example of DDL for sources, and given that we can have all these streams with data, with heterogeneous data, but we can join all these streams, we can aggregate them, we can calculate various things, and we can even do complex event processing. So practically it means that we can track withdrawals, for example, from Tornado, Fixed Float, any funding that allows malicious actors to receive this funding anonymously. Then we can track further. We can track which contracts they deploy which intermediate addresses they use to hide their traces. We can calculate sums of transfers inside transactions, and we can match specific call traces inside these transactions, so we can find known patterns of exploits. This is an example of a rule in our system. You don't have to build a project for that. Like in Forte, you don't need to build a bot. You just write like 10 lines of SQL, and you can achieve all the same functionality. So in this example, we look for events when a contract emits an upgraded event and then just self-destructs. It's a non-vulnerability in all the Open Zeppelin contracts using an upgradable pattern. And this is a more complex example. It uses CEP, complex event processing, to detect sequences of calls inside call traces. In this example, we detect an reentrancy. We just look for selectors that are known which are used to receive callbacks. So we firstly observe this callback and just basically make a tree. We observe a tree of calls inside all the call traces. So this rule is very effective to detect reentrances inside call traces automatically. This is how it looks like in practice when we detect an exploit by looking at each call traces. So we basically observe a callback, then see that it callbacks again into the contract, and the contract calls our exploit again. So the results, we deployed all this pipeline in Amazon, and right now we receive real-time alerts in our dashboard as well as in threat intelligence feed and Telegram. We extract and analyze all the transactions and all the data from Ethereum mainnet and Binance Smart Chain networks. And so far we have detected more than 50 exploits since May, including Curve 0 day. And I was astonished personally at how many exploits are not visible at all, not on Twitter or in any Telegram groups. They are not so big, but they are happening constantly, and without such tools you cannot just spot them. And one of the success stories that we prevented a hack on Fortress protocol, I guess 2 or 3 weeks ago. We observed that there was a malicious governance proposal that was aiming at taking over these protocol funds. So we reacted quickly, approached the team, and they stopped this proposal. So that's it. Thank you for your attention. Any questions? No.
Thank you for your talk. I was fascinated that you built on GigaHorse and you wrote Datalog. Can you give us an idea of what exactly you wrote in the rules?
Yeah, first of all, thank you for this great tool, because I didn't see any tools that could achieve what we wanted to do. Well, your tool is built on Datalog. I guess you're the experts in Datalog, unlike us, because it's fairly new language for us, but we try to implement some stuff to detect exploits. Namely, we made some analysis to extract self-destruct opcode. I mean, the presence of just self-destruct inside the contract, as well as create two opcode, because this is a very important indicator of some exploits. For example, tornado cache governance hack. And I must say that there are lots of data already extracted in GigaHorse. You just need to look for all the text files that are generated, and most of relevant stuff for us is already located here. For example, external calls. So we just needed to parse the data that is already extracted by GigaHorse. But yeah, we will be, I guess, extending some of this analysis, but we will need to learn more data log, I guess.
Okay, then no further questions. Thank you, Arseny.
Thank you very much.